Welcome back to the part 2 of achieving artificial intelligence through process innovation. In the previous part, we took one ordinary motor. First, it simply rotated, then it's controlled it, then we sensed it, connected it, monitored it, and predict the failures and the recommended action. And finally, we imagined a system that could adapt its operating condition. But now I want you to make problem much bigger. So one motor is not a factory, and one motor is not a industrial IoT. It has one dashboard is not a smart manufacturing. One robot is not a intelligent part of the production system. One AI model is definitely not an intelligent ecosystem. So here is the real question: how do machines, sensors, and robots and network data, so artificial intelligence or human judgments and adaptive actions, becomes one integrated data manufacturing intelligence? To answer that, we need to stop thinking about AI as one isolated tool. We need to think in a layer. So that's the slide 12 tell about the smart manufacturing technology. So look carefully at this architecture. This is where many AI decisions become incomplete. So people directly jump into the machine learning or deep learning or generative AI analytics, but in a real factory or a real scenario, intelligence cannot finally flow in the air. It needs a physical foundation. So let us build the foundation. It's an intelligent factory, layer by layer. So look into the slide again. The physical layer point to the bottom layer point, the foundation. We have the physical world, machines, robots, CNC machines, motors, and the robots, the CNC plus robots plus motors, and production line linked together. Motor rotates, the productions of manufactured. And here is the important point: if you do not understand the physical process, every layer above it becomes vulnerable. So wrong process understanding or wrong sensing leads to wrong data, and wrong data gives the wrong predictions, and weak predictions is a poor decision. So intelligence begins with respect. So for the physical reality, we need to check the second layer, that is a sensing layer. Sensing layer, it's look into the sensing the temperature, vibration, or a vision form, or a current, how much current is there. The physical property, this physical process is happening continuously, but unless something is observed, the process remains invisible, and it's not digitally systematic. So remember what I said earlier, the first sensor is the human attention. But when continuous observation is required, engineering sensors becomes the essential one. Thermocouple doesn't understand the temperature, and accelerometer doesn't understand the bearing failure, and a camera doesn't understand the quality, or the sensor creates signals, and the intelligence requires the context. It's a very important one. Layer 3 is a connectivity layer. Next, connectivity is the industrial. It's not a industrial IoT without connectivity, and industrial network, it is one of the main thing. The edge connectivity. Now isolated signals begins moving, machines to gateway, and sensors to the edge device, and PLC to the SCADA, and equipment to the server, the factory to the cloud, and machine to the machine. But I want to challenge one common misunderstanding. Connection does not automatically means intelligent. If you connect 1000 meaningless signals, it doesn't have an intelligence. It doesn't create an intelligence also. I may be created 1000, but it's created connecting the problem only. So the data layer is a very important one. Data is a historian database, contextual data, and here I want researcher to listen carefully. Raw data is not automatically useful knowledge. Suppose the vibration is 6 millimeter per second. So once we get the data, good, but it is because of what reason? It's because of what RPM it is running, under what load, in which bearing condition, in which operating mode, before or after the maintenance, at what temperature it is running, or with what production variant it is measured. These are all some important points need to be remembered before taking the decision. Same numbers or different context, because in different contexts the numbers will be vary. So different meaning and a different context, we have the different digitally impressive but operationally weak if we take the decision without the context. So another strong thing is intelligent layer. Now AI, machine learning, analytics, optimization. Notice something, AI comes here not at the beginning of this architecture. So below AI, the physical process, the sensing, the connectivity data, and this is exactly why my AIPI model begins earlier than the algorithm. So before going to the algorithm, this basic AIPI model is very important, because the intelligent layer depends on the quality of the journey below it. So the layer 6 is a decision layer. Next, human plus AI decision support. This layer is extremely important because a prediction alone is not a business outcome. Bearing may fail even in 7 days. Fine, what should we do? Stop now? No, we have to continue the production. So reduce the load, wait for the planned shutdown. So we should not shut down immediately, we need to plan for the shutdown. So order the spare parts, inspect, and when it is ready, we'll start the action. Technically correct prediction may still require some operational judgment. So economical judgment and safety judgment, ethical judgment. The prediction is not the end of the intelligence. The decision quality matters. So next we move on to the final action layer. It's very important. Finally, adaptive manufacturing response, adjust the speed and modify the path and redistribute the load and trigger maintenance, correct process parameters. And now the information returned to the physical world, physical process and sensing, continuity, data, intelligence and decision action. And action creates a few physical conditions which create new data, which create new learning, and that is when architecture begins to behave like a loop, not merely like a stack. So in the doctorate level insight, this is the step-by-step data, intelligent decision, action, and research provocations. It is very important for the researchers. Here is the question for you. Is manufacturing intelligence located in the AI model, or does intelligence emerge from the interaction between physical process, sensing and contextual data, and prediction, human judgment and adaptive action? That question seriously interdisciplinary research. Let's move on to the slide 13. It's based on manufacturing technologies. Now let us identify the seventh technology. Number 1 is smart manufacturing. Number 2 is intelligent robotics. Number 3 is industrial IoT. And number 4 is digital twins. And number 5 is predictive maintenance. Number 6 is machine vision. And number 7 is AI assisted engineering and decision warning. But here is the mistake. Many organizations ask which one should we start first. So we need to buy. Should we buy IoT or should we buy AI? Should we buy the digital twins or should we buy robots? Technology is not a grocery shop. The real question is what problems are we solving, because the process have many problems inside, and how should we this technology integrate, and because of the competitive advantage comes not for one technology but for the intelligent integration. That is your exact slide 13 is a key message for that. So now I will show you interesting, that is evolution of the factory can be the understand from the question it is capable of asking, smart manufacturing. So then we go to the move on to the slide 14. It is a smart manufacturing. Imagine 5 factories, same products, same industry, but very different level of intelligence. So the factory 1 is a traditional one. Ask what happened, machine stopped, defect occurs, and delivery delay, bearing failed and energy is increased and overheat and generated. After the event, we investigate and then find the historically find and correcting the problems. The factory 2 is a connected factory. Ask what is happening, and current temperature, current production, current vibration level, current downtime, current quality, everything will be visible, and it is displayed in the dashboard. So factory 3 is a predictive factory. Ask what happened, what will happen, and what learning fails. Will the quality drift? Will the demand exceed capacity? Will the tool wear, cross the limit, cross the tool life, or something like that? We move this observation towards the anticipation. So when it comes to the factory 4, the intelligent factory asks, what should we do next? It's need to reduce the load or change the frequency, or schedule the maintenance, or adjust the parameter and reallocate the production. Now the prediction begins influencing automatically. Now we moving from the visibility towards the autonomies of the manufacturing intelligence, evolve from the visibility to the autonomy. So your slide 14 follows the exact progressions. If you are working in a factory, ask yourself, which question can your factory answer today? What happened? What is happening? What will happen? What should we do? Or can we optimize automatically? Or please write your commands so I can look into it and answer it. So my experience will guide you in coming out of your problems. So let's move on to the slide 15. It's an intelligent robot. So now let us talk about the robots. Traditional robots, very powerful, very accurate, and highly repeated. It will do only the repeated task, but usually pre-programmed and fixed task only given to that structured environment. Put the commands here, pick here, move there, or something like that. So example, build this path, repeat. So it will repeatedly build the path. Very disciplined employees, no tea break, no Monday mood or something like that. Limited contextual understandings, but here we need the intelligent, that is robotics, move towards the different capabilities, recognize and adapt, and collaborate and optimize. Real application, AI pick and place robots is the main used in this type of application. Suppose the component arrive with a variation. Suppose the process 1 is not delivering the part yet. So the vision identifies the part is empty means it kept idle, the cycle will not run. So here the vision play a major role. Robot changes, pick the coordinates, that is the difference from the fixed to the repeated vision guided robots. So camera or a sensor, vision sensors, it interpret the robot act, adapt and assemble. Sometimes there is a part variation occurs, the process adjusts, and the intelligent welding and vision or a sensing identifies the seams conditions and the parameter response. So here the parameters play a major role. So autonomous material movement and AGV and AMR perceives the environmental planning, and it understands the situation and it responds to the obstacles. So the next generation robot will not only execute, it will interpret the context. That is exactly the key message in the slide 15. So researchers looking here is the difficult question: how much adaptation is enough before we call a robot intelligent? If a robot change path based on the sensor, is that intelligent? Is it safety? If it recognize the object, the intelligence. If it learns from the repeated outcomes. So intelligence, again, intelligence may not be a binary. It may exist across the level of the capability. That is the context. So let's move on to the slide 16, industrial IoT. So this is shorten our material movement. We can operate from a distant place. Any maintenance or any immediate action need to be done can be immediately solved using the IoT. Imagine a machine is running internally. The temperature is changing, the pressure is changing, the vibration is changing, the current and changing the speed, changing the position is changing, and the force is changing, the quality condition is changing, and many changes are there. The flow is changing. The machine is continuously experiencing the reality, but can it communicate that reality? That is where the industrial IoT becomes very powerful. So the industrial IoT is a chain of physical events. The sensor, edge device and network, and make a data platform, and the analytics, decisions. So let's take one example. The bearing is degrading, the physical event, and the vibration signature changes, and the sensor accelerometer detects the signal. The edge device filters off the processing the data, and the network communication relevant, and the information or a data platform stores and the contextuality, and the analytics detects the abnormal pattern, and the decision inspects maintenance and reduce the bad, and if it is good it will continue, if it is bad. So now tell me, where is the intelligence in the sensor or edges or the network or the analytics or a decision? Again, perhaps the meaningful capability emerges from the complete chain. So it is an important industrial warning, but please remember, more sensor do not automatically create a smart factory. Do not create the dashboard, do not automatically create the better decision. More cloud data do not automatically create the intelligence. A machine cannot meaningfully participate in the intellectual ecosystem, but the data with the purpose can create noise at the scale or very strong lines. The slide 16 claims the physical event through the sensor, the edge device, network platform, and analytics to the decision. So working on IoT, tell me in my comments what is your biggest challenge, or sensor reliability, any connectivity, or cyber security, or a data quality, or integration scaling. I want you to know what the real engineer are facing, but what we face, we have a solution. There is a website, we have a group or IEEE, or we can use those platform, and we can find the standards, and we can easily implement those standards in your process. We can even copy the method. That's a process innovation. Let's move on to the slide 17. Digital twins. This is a very interesting topic. Now we come to one of a fantastic technology in the modern engineering, that is digital twins. First, one clarification. There is a 3 beautiful D model. Rotating on the screen is not automatically a meaning digital twin. It's not like that. Or any 3D or CAD model, valuable simulations, valuable dashboard, but not a meaningful digital conversion, usually requires a richer relationship. So physical machine, robots, production line, real equipments, data collection, operation information, all or the state conditions, or a parameter, or an event. Physical reality begins with the digital representation. So digital representation model is a simulation, state estimation, and behavioral representation. Now the digital counterpart can help us understanding the it's not merely the asset look like, but potentially how it behaves. It's very important. So intelligent predictions, optimization, and digital support. And now the possibilities expands: visual commissioning, the performance monitoring, and failure prediction, the process optimization, what if analysis. It is the variation. It has to be recorded, monitored, and it has to be take decision immediately. So the real industrial story. Let's imagine a production line, management task. Can we increase the output by so much, or 15% or 20%, say digitally? Traditional approach is change physical line, try, observe. So maybe the success, maybe create another bottleneck. So digital twin oriented approach is very important. The present current system, test the scenario, change buffer, change the cycle time, change the robot sequence, change the machine allocation, and observe the prediction and consequences. Before disturbing the process physical world, exploring the possibility in the digital world first, and then you implement it as a digital twin. It is a best method of practice. The researcher terminology is easy. The validation is very difficult. The future belongs to those who prove the relationship between the model and the reality. For the slide 17, it explicitly limits the physical asset, the real-time operational information, or a digital representation, and the intelligent for the prediction, optimization, and the decision support. So let's move on to the next slide. It is slide number 18, predictive maintenance. We already discussed about this predictive maintenance. We are not going to stop the machine and do the maintenance immediately. Now let us talk about the maintenance. Every industrial person watching this know the pain of the breakdown. Production stops, customer waiting, maintenance searching the spare parts, unavailable, and the management asking how much time is needed. They smile. The maintenance engineer gives a dangerous answer. Sir, just 10 minutes. After even 2 hours later, he's telling just 10 minutes because he's trying to cope up. He's trying to patch off, but he don't want to make a complete solution because he want to run the machine immediately, but it is not a true thing. Actually, needed is a permanent action. So permanent action needs some time. So he cannot go and get the material immediately, or he cannot go and solve it immediately without proper step-by-step actions. So every 1,000 hours need to be some of the preventive time should be there. So we need to stop the machine to do the preventive maintenance, better planning, but possible problems, we may replace the healthy components, or failure may occur before the interval. So condition based or condition change, vibration rises or temperature increases, so oil condition change, the current signature change, then the maintenance respond to the actual condition. So the level 4 is the predictive EA estimation, the failure probabilities simply bearing bad, but perhaps based on the current degradation pattern, failure is increasing. Now maintenance planning changes, the prescriptive system recommends. So we have the recommended the replacement cycle for each and every products. So we need to keep the life cycle and we need to change it whether the machine stops or not. So that is the best way of practice. So it's adaptive. Now imagine the system optimize the response, the production schedule changes, and maintenance window adjust, and spare parts planned updates, and operating conditions adapt. So the future maintenance engineers manage probably the risk and intelligence, not only breakdown. That is exact conclusion of your slide 18. So the predictive maintenance is very important. I want you to ask some deeper. If an AI model says failure probably B2 percentage, or something like what should the engineer do? Stop the production or continue? Inspect or reduce the load? So what is the cost of the failure? So everything need to be analyzed. We have a digital twin to support this predictive maintenance. The AI model, it is a decision problem. It's uncertainty. So anyone have any doubt in this subject, please comment in this comment section. I will get back to you. Okay, let us connect what we have discovered. Intelligent factory, it is very important. The physical layer, sensing, connectivity, data intelligence, and decision actions. It is a step-by-step process. The smart manufacturing, from what happens to what is happening and to what will happen in future, to what should we do, to can we optimize automatically, or these type of things will be coming there. So intelligent robots for the repeatability or towards the adaptability. Industrial IoT gives machines a digital voice. It is very important. So when we think about the digital twin, the connective physical reality with the digital representation. So predictive maintenance, moving from repair after the failure, instead of that towards acting before the failure. So now something is still missing. That is, a factory can sense, the machine can communicate, and digital twin can represent. AI can be predict, but what can the system see? So it is a very important one. So what is the system is watching? It is a very important. that is the machine vision. So in the next session, we give the manufacturing system the ability to see, that is the machine vision. Don't miss this opportunity to see the machine vision in the next episode. Then we confront one of the biggest question in the artificial intelligence, that is human or AI. So my answer is neither human or AI, and from there we will enter the emerging industry 6 thinking, the exploratory, that is the imaginative or predictive industry 7 vision. The deepest is very important. In my question is the entire master class we will go through that. Can the future industry become not only the smarter but also wiser? Continue watching Innovators.